Hello and welcome to this video on thermal energy. This is a topic from Unit 5 of the AQA Physics A-level course, looking at thermal physics and thermal energy. And we're going through this with a view to taking our A2 Unit 5 exam. There's a couple of things I'm going to go through in this video. First of all, a general discussion of thermal energy, trying to come up with a definition for thermal energy, and perhaps thinking about some of the calculations involved in terms of changes of energy. Then after that, we're going to have a look at the idea of temperature and how it relates to thermal energy, and a link between temperature and energy. We've got this equation here which we're going to become familiar with, and lastly we're going to be looking at the energy and temperature changes involved and the peculiar nature of changes of states. So what actually happens energetically speaking and energily speaking, no, that is energetically and energy speaking, when we change from a solid to a liquid and from a liquid to a gas and vice versa. Okay, so the first thing to note here is that energy is a pretty abstract concept, but we are going to be dealing with thinking about energy changes and what happens when something hot transfers energy to something cold. This is one way that we can transfer energy, or another way that we can transfer energy is when something exerts a force. So I'm going to kick this football. So one thing exerts a force onto another thing and gives it some energy. So afterwards here we've got our ball. No, it's the same ball, it's got a star on it, must be the same ball. And now it's got some energy. So these are two ways that we can transfer energy. Energy by transferring heat, and energy by applying a force. Okay, so in terms of something's internal energy, hot things have quite a bit of internal energy, and they naturally transfer that energy to their less energetic surroundings. The way that we deal with this energy is by coming up with a temperature scale and saying, oh, this is this hot, and that compares to these other surroundings which are these hot. But really these temperatures and it's a way for us to deal with internal energy on a day-to-day basis. Something for us to be aware of though is that temperature and internal energy do not always equate. So it's possible for you to have something that was at a lower temperature but actually stored more energy than another object. Right, so whilst I was waffling on there, you can see I've been struggling to delete. There we go. Okay, so take this for example, right? We've got, and you're going to see it once I've drawn it. Oh, a lovely hot bath. Here we are. And we've got a big bath. We've got here 100 litres of water, and it's at a nice temperature of 20 degrees Celsius. Oh, lovely. Isn't that nice? And over here I've got a kettle, and my kettle, little mini kettle, it's just a 1 litre kettle, and I've boiled it, and it's at 50 degrees Celsius. Which one's got more energy? Well, this one's definitely hotter. But actually in terms of the energy that is stored, if I were to transfer all of the energy from this hot bath of water, if I were to transfer all of the energy from this 1 litre of water, we might actually find that this is a larger store of internal or thermal energy, because this one's got 100 times the amount of particles inside, and all of the particles inside here have got lots of energy. Yes, no particle in this bath will have as much energy as the most energetic of particles inside this kettle, but the total amount of energy from all the particles in this bath is more than the total amount of energy from all of the particles in this kettle. So that's a distinction that we need to be happy with between temperature and energy. So let's have a look at the idea of thermal energy. Thermal energy is the energy of an object due to its temperature. So it is equal to the sum of the random distribution of the kinetic and potential energies of the object's molecules. So if our objects have got lots and lots and lots and lots of energy, that manifests itself as that object appearing to be hot. The molecular kinetic energy increases with temperature. So we heat something up. If we transfer some thermal energy to something, its kinetic energy increases, its potential energy increases, and that physically manifests itself as its temperature appearing to increase. The potential energy increases if an object changes state from a solid to a liquid or from a liquid to a gas. Now this is because our particles are further away from each other, and particles that are far away from one another have a higher level of potential energy than two particles that are close together. So if we consider here a gas, right? A gas has got, and say we're talking about the same amount of matter. So here we are, we've got 4 particles in my gas, and each particle is zooming round really, really fast. We've got really high kinetic energy, and we've got high potential energy because they're all far apart. In my liquid, and again we're looking at a 4 particle liquid here, yeah, they're vibrating around a fair bit. They've got a bit of kinetic energy, not so much potential energy, a bit, but they've got some kinetic energy. Now let's look at Mr. Lazy Old Solid over here. Here we've got very rigid structure, as closely packed as we possibly can, very little potential energy at all. Oh, actually I've drawn that a bit energetic there. There we go, we've got some tiny little vibrations going on here inside our solid. Yeah, am I energetic? Not really. I've got low thermal energy. Low thermal energy solid, higher thermal energy liquid, very high thermal energy gas. Okay, so temperature. Temperature is a measure of the degree of hotness of a substance. So it is not a direct way for us looking at the amount of energy that a substance has, because temperature is dependent on the volume and the state and the situation that amount of stuff is in. Heat energy normally moves from regions of high temperature to lower temperature, though. This is why temperature is important. It's something comparative. Two objects are said to be in thermal equilibrium with each other if there is not a net transfer of heat energy between them. So if we've got two things that are not transferring heat energy to each other, so look here, I've got my nice big bath with 100 litres of 20 degrees Celsius water, and my kettle here has cooled down now. I've got 1 litre here, it's at 20 degrees Celsius. If I plonk my kettle in the bath, obviously I've unplugged it because I do not want to electrocute myself, and we always take our safety very seriously. But anyway, yeah, look, I'm going to put my 20 degrees Celsius kettle in the bath. They will not transfer energy from one to the other because they are in thermal equilibrium with one another. But let's say I've got a kettle here that I have heated up. It's only 1 litre, but it's now at, I don't know, whatever, 70 degrees Celsius. Of course, it's unplugged because we take safety very seriously. Plonk it into the bath, and what's going to happen? Some of this energy from my bath is going to transfer, and it is going to cool down this kettle. No. Is it going to cool down? The thermal energy, oh, I'm talking nonsense. The thermal energy from the kettle, it moves from the hot region, as it says here, energy moves from regions of higher to lower temperature. So this kettle is going to lose its energy into the surroundings here. Now, this was at 70 degrees here. It will equilibrate with the large amount of cooler water here. So this is going to go from 70, it's going to lose all of its heat until it's the same temperature here. So what we might get, I'll just draw the situation down at the bottom here, maybe this whole bath, 100 litres, maybe its temperature will increase by 1 degree rather, and the kettle it will drop down to 1 degree. But either way, they're now in thermal equilibrium. We've got no net transfer of heat from one to the other. Okay, so substances can store energy, and heat is, or thermal energy is one way that they do that. We use temperatures to talk about how hot is one thing compared to another. That's not necessarily saying how much energy it has compared to another thing. Alright, so temperature scales, they are defined by two fixed points, and they are standard degrees of hotness which we can measure accurately. What is this talking about? Well, we've got different ways of describing how hot we think one thing is. One of those ways that we use fairly frequently is the Celsius scale. We're going to give it the symbol theta. Units are degrees Celsius. This is a system that humans made up. And we were like, oh, well, how hot's this thing compared to that thing? Well, this one's pretty hot and that one's not that hot. That's not very scientific. Let's put some numbers on this. Let's say, well, let's use a physical constant. Let's use something from nature that behaves itself similarly all the time. Ice, right? If we've got the exact point, the melting point of ice, that is always the same no matter where we look at it. Let's call that 0. That's 0 degrees Celsius. And what happens at the steam point when water starts to boil? So we've got our beaker, it's getting hot and it's just starting to boil. On the cusp of that point where it starts to boil, we are going to define that as 100 degrees Celsius. And then anywhere between 0 and 100, well, let's split it up into 100 parts, and that way we've got, you know, enough sections between 0 and 100 for us to work and for us to use it quite comfortably. And that's a scale, and we use it, and it's quite handy, especially on our day-to-day existence. But it's misleading because this 0 value here, this suggests, well, 0 suggests that there is no temperature here. This suggests that ice is 0, and that suggests an absence of internal heat, which we know cannot be true because it's possible to go lower. We know that we could remove some more heat energy from here. Let's take some more heat out of this system. We know we could get our ice actually down to degrees of, you know, -5 degrees or even -10 degrees. We know that, you know, in Russia in the winter they often have days of -20 degrees, -40 degrees up at the North Pole, which is pretty cold. And we can go out. What happens if we start, you know, if we go up into space? How cold is it out in space? It's pretty dang cold, as they say, -200 degrees Celsius, which is, oh, that's also, we can also do stuff like with liquid nitrogen. And liquid nitrogen, we can get it down to about -270 degrees Celsius. So actually this 0 degrees is a bit of a nonsense. It works for us with water. It's basically the water scale. But it is nonsense. What would be better is if we have an absolute scale. And we call it the absolute scale because we've got, well, it's the absolute scale or the Kelvin scale. It makes sense because at 0, this is no heat. So the 0 Kelvin mark is the point at which there is absolutely no heat. And this happens to be the same as, or equivalent to, -273.15 degrees Celsius. So if we started here, thinking back to our Celsius scale, we've got ice, which is 0 degrees Celsius. It's possible to remove heat from this system until we get to a point where there is absolutely no heat whatsoever, and that is 273.15 degrees Celsius lower than 0. This is 0 Kelvin, and this is the absolute scale, absolutely 0 heat. So this point here, 273.16 Kelvin, well, if -273.15 is 0 Kelvin, 273.16 is actually 0.01 degrees Celsius. And we've got this discrepancy here between this 5 and this 6. the 5 and the 6 there, that is the temperature at which pure water exists in thermal equilibrium with ice and water vapor. So it's an interesting point, because actually at 0 degrees Celsius it's possible for us to get water in the form of ice, liquid water, or gaseous water, depending on pressure, pressure and volume, and some other factors. But this is an interesting point for us, and it's a different scale that allows us to look at something a little bit more sensible than saying 0 degrees Celsius, which is silly. We've got here a no heat 0, absolute 0. There is absolutely no heat here. One point to note here, though, is that this is a theoretical value. That does not exist in nature. So everything I was just saying about the 0 degrees Celsius seeming like a silly thing, now maybe you might think absolute 0 is a silly thing because it doesn't exist. And basically, physicists have never found a situation where you can totally remove all the heat or all the energy from a system. We always think there must be some tiniest amount of energy, but at least it's 0 where we mean to have a 0, and that 0 in that context does make sense. Equivalence between these two scales. This should be very straightforward for us to do. Let's have a look at this picture here. We've got here the Celsius scale and the absolute scale, and we're seeing how they compare to one another. At minus 273 degrees Celsius, we've got 0 degrees Kelvin. At 273 degrees Kelvin, we've got 0 degrees Celsius. And at 373 degrees, oh sorry, not degrees Kelvin, just Kelvin, we've got 100 degrees Celsius. So these are two scales that cross over and are useful to us. We could also sort of try and look at this graphically. Just quickly, I'm going to jot a little graph here just to show how these two things might overlap. So imagine we've got a scale here. So on the side here we'll do temperature. This could be 0 degrees Celsius, which is also, what am I doing here? 273 Kelvin. And back down here we've got minus 273 Celsius, which is 0 degrees Kelvin. And here we could have 100 degrees Celsius and 373 degrees Kelvin. Now I've basically just drawn the same thing here, but what we could have up the side here is what is the pressure of a gas at these temperatures. Now at 0 degrees energy, let's change colour. What colour should I do? Yeah, I'll do a red. At 0 Kelvin, there is going to be 0 pressure. It's got no energy, there's no force, the particles are not moving at all. We're going to have a linear relationship, boom, like that, for one gas. And another gas, a different chemical element, might behave slightly differently, but we're going to have straight lines here, which are dependent upon the substance. At 0 degrees they behave one way, at 100 degrees they behave another, but all chemicals, all gases will come back to this point of 0 pressure at 0 Kelvin, because there is no energy. So if it's got no energy, there are no particles moving around, it has no energy, it's the complete absence of energy. Hopefully that makes sense. Does that make sense? If it doesn't make sense, go back and listen to what I've said already again. Should we go back and have a look at what I've said? Yeah, go on, let's go back and have a little look. We've got thermal energy. A substance has heat, and that heat is due to the fact the particles inside it are moving around. If we remove all the heat, then they've got no vibrational energy, no kinetic energy, and no potential energy. and this is called absolute zero energy. This occurs at 0 Kelvin or minus 273 degrees Celsius, and that is thermal energy. How can I heat it up? Well, I could transfer some heat. That would be one way that I could do it, or I could do some work on it. I could give it a good kick. Now obviously this is maybe a bit of a metaphorical kick, but I could do some sort of mechanical work on it. This is a leg, and this is a foot, and this is a kick. And if then the whole thing was moving, it's got some energy. And obviously when I kicked it, we'd get a bit of vibration going on inside. So now it's not at absolute zero anymore. Yeah? And then if I wanted to cool it down, well, I could take some heat out of it, or I could let it do some work on another object. So let's say I had a toy person here. It could do some work. Then it would lose that work. So now it would have some potential energy, it would be moving, and this would be back down to zero. It wouldn't have any energy anymore. Okay? That's thermal energy. Done. So, different objects have energy, internal energy. And let's think about the idea that we might want to transfer some energy between two objects. So, I didn't mean to show you this slide. Ignore this slide. And look at this slide, which is blank. Completely blank slide. Right, so let's make a fire, and this fire is giving out heat energy. Okay, and I am going to put in the fire a big lump of copper. What we're going to have a look at is how does this copper change when it is subjected to heat. If I can get some heat energy from some source and apply it to this copper, what's going to happen to the copper? Well, it's going to be gaining energy. And if it gains energy, deep inside the copper, what's happening is that we've gone from having our little copper particles all here, sort of, chilling out at room temperature. These copper particles, when we apply some heat, they're going to start vibrating more and more and more. If we apply enough heat, they might even start trying to liquefy. But for the time being, let's think about what's happening. Well, they're starting to vibrate more and more and more and more. And the physical manifestation of that is that we get an increase in the temperature of our copper. So if we apply some heat energy to a piece of copper, its temperature increases. But what I'm also going to do, let's imagine here that I could also get this exact same heat source. Copy. Right, so you've got to bear with me a second here. This is my first time of trying to muck around with this stuff, so I'm bound to make a few mistakes. Right, let's group this. And now let's get ourselves a second fire. Okay, so now I've got two fires and two lumps of metal. But this one is steel. So, oh, not steel, iron. I've got some copper, I'm going to heat it up, we get an increase in temperature. I've got some iron, I'm going to heat it up, we're going to get an increase in temperature. Are they going to heat up in the exact same way? No. Why not? Because they've got different properties. they've got different physical properties. The way that the atoms inside a piece of copper relate to one another is different from the way that the atoms inside a piece of iron relate to one another. So we get a different effect. How much are they going to heat up by? Well, it depends on the properties of the iron particles. It depends on the properties of the copper particles. And what we find is that the change of heat energy, so the amount of heat energy here that's being given out, the way that it affects this system, we're going to use this formula, mc delta T. How much the copper and iron going to heat up? It depends on this. Let's introduce ourselves to the specific heat capacity C. So this is the formula I just showed you. Delta Q is equal to mc delta T. Let's have a read. The specific heat capacity C. Who missed out a comma there? Look at that. I didn't do that. Got this slide from somewhere. Come on. Ooh. What I'm doing here is I'm doing this all by hand. Oh dear. Right, I'll use the keyboard. Right. Let's pretend I didn't do that because that's a bit distracting. So, how much heat energy is transferred? How much temperature are they going to increase? The change of heat is related to the change of temperature, and it depends upon two constants here. M is the mass, and C is this thing called specific heat capacity. So, let's have a look. The amount of energy in joules is related to the mass of the substance in kilograms. So we could imagine here we've got a kilogram of copper and a kilogram of iron. That would be easy. The temperature change, which is measured in Kelvin, and 1 Kelvin is the same as 1 degree Celsius, it depends on this thing called the specific heat capacity. And the specific heat capacity is different according to what the properties are. It's different for different materials, and it is defined thus. A specific heat capacity is the energy required to raise the temperature of a unit mass of the substance by 1 Kelvin without change of state. So we're not going between solids, liquids and gases here. This is how much energy do I need to give my copper to make 1 kilogram of that copper increase in temperature by 1 degree Celsius. Or, for iron, how much energy do I need to give to my iron in order to increase 1 kilogram of iron by 1 degree Celsius? So, if something's got a high specific heat capacity, it takes a lot of heat to raise it, or to raise 1 kilogram of it by 1 degree temperature. If it's got a low specific heat capacity, it does not take much heat in order to increase its temperature by 1 degree Celsius for 1 kilogram of that object, of that thing. Bloody bloody blah. If the temperature is measured in Celsius or degrees Celsius, the specific heat capacity is its joules per kilogram per degree Celsius, or joules per kilogram per Kelvin. They're interchangeable. So how much energy is required to increase the temperature of this iron or of this copper to increase 1 kilogram of that material by 1 degree Celsius? So let's just look at a little example. Let's say that I had something, let's say I've got material X. Okay, and I'm going to give it 100 joules of energy. And I've got 1 kilogram, let's see, C. And let's say if I heated this up by if I heated up 1 kilogram of it and I gave it 100 joules and I measured that its temperature, its change in temperature, so let's say it went up by 4 degrees Celsius. Well, that is the same as saying that 100 joules, 1 kilogram times 4, well that's 4 kilogram degrees Celsius times C. Okay, so we've got 100 divided by 4 is going to actually give us the value of C. So here, C is equal to 25 joules per kilogram per degree Celsius. What this means is for material X, in order to increase 1 kilogram of material X by 1 degree Celsius, you are required to supply 25 joules of heat energy. And that is what the specific heat capacity is. So different objects have different specific heat capacities. Metals tend to have quite a low, they have a low specific heat capacity because they're really good conductors, they're very good thermal conductors. Because there are very few impurities and because they tend to share electrons very easily, you apply it some heat, that heat spreads out, it warms up. They're not insulators, they're conductors. Let's try heating up some wood. Well, it actually takes me a lot more heat energy before that heat can pass through the wood. So insulators have very high specific heat capacities. Water has a very high specific heat capacity because partly because it's a liquid and the molecules inside the water are not very close together, but actually water is not a very good thermal conductor. It's a much better conductor of electricity. It takes a lot of energy comparatively to heat up water than it does to heat up metal. How do you measure specific heat capacity? You could do an experiment, and I think the guys in my physics class have actually done this already. Here we've got a setup. We can heat, using a heater, a piece of material, and we can measure its temperature. Connect it up in a circuit thus. So you've got a power supply and a switch. You've got a rheostat here, so we can adjust the resistance if we need to. And it goes through a voltmeter and ammeter. Use the voltmeter and ammeter to work out the power is equal to V times I. So we can work out the power. We can time how long we do it to work out the amount of energy going through. And during a set amount of time, we can see what is the temperature change. So how much energy is applied, what is the temperature change, what is the mass. If we work out the mass of this object, and we can go back and from there find out what is the specific heat capacity of it. Same thing goes for water. Exactly the same idea. We can do that. One thing here is that if you do it for the specific heat capacity of a liquid, is that we might also have to work out how much heat is absorbed by the container in which the water is contained. So it would be a good idea, excuse me, to try and do it in an insulator, which is why they've got this liquid on points not in contact with the thing around it, because if it's in contact with the thing around it, its thermal conductivity, it's going to lose heat to the surroundings or to that object. So specific heat capacity, how much heat does it take to raise 1 kilogram of a substance by 1 degree Celsius? Specific heat capacity is equal to mc delta T. Now obviously a couple of questions about heat and internal energy applied to this, and then you've got to do some sort of calculation with some material, work out the specific heat capacity. They're probably not going to give you a nice easy one where you've got 1 kilogram, because that would be too easy, and there might be some sort of trickiness about working it out whether it's in Kelvin or degrees Celsius, but otherwise, you know, there's not really that much that they can do on this. All right, don't look at that slide. Do not look at that slide. Did not mean to show you that slide. What I meant to do is give you a nice new blank slide like this, and we're going to talk about what happens over time when I start heating up some water. Oh no, actually I'm going to start with some ice. So here I've got some ice, and let's say that I start off at 0. No, I'm going to start off sub-zero. Let's say I start off at minus 10 degrees Celsius, because I can. Right, I have got my ice, and what I'm going to do now is I'm going to heat up some ice because that seems to be quite good fun. All right, I'm going to heat up some ice, and I'm going to be applying or constantly applying some heat to this ice. I'm going to observe what happens to its temperature over time. This process for ice, it is worth noting that C for ice is equal to about 4,000 joules per kilogram. Oh, it's not much room there. So specific heat capacity of ice, look at that, I'll mark that up. Specific heat capacity of ice, 4,000 joules per kilogram per Kelvin. What happens with water or ice? As you heat it up, it gets hotter and hotter and hotter, and then when it gets up to about 0 degrees Celsius, it changes state from a solid into a liquid. And during this time, when it starts changing state, what happens is this. And then it's a liquid. Keep on heating it all the way up to 100 degrees Celsius. And what happens is this. At these points where we've got a change of state, at either the melting point or the boiling point, as you increase as you keep applying heat to it, there is a time during the change of state whilst it does not get any hotter. So even though we're constantly applying energy at the same rate to our ice, or here constantly applying heat at the same rate to our liquid, they do not get any hotter. This is the change of state. This heat here and this heat here we call the latent heat. This is the heat energy that is required to induce a change of state in a solid or liquid. The energy required to change a state in melting or boiling. Latent means hidden, because the heat energy supplied during a change of state does not cause any temperature change. So this is a phenomenon that is observed in any material when it goes between solid, liquid and gas. So this is whether you go from cold to hot or from hot to cold. The same thing would happen. So if the time actually on this slide was running, so say we crossed this out and did our time going backwards, and we were starting from a gas and we were removing heat from it and cooling it down, same thing would happen. Any change of state, so let's say, look, time here is 0 and time here is 100 million hours, or just 100 hours. We're doing it really slowly. We're taking heat out of this and it comes down to a liquid, and along this bit here it's all a liquid. There is still this latent heat between this change of state. It happens both directions, whether we're going from ice up to a vapor, from a vapor back. So look, some key terms in here you need to know as well. I'm not going to go through this because you just need to know these things. From ice to liquid, it melts, evaporates to become a vapor, condenses or freezes. From ice straight to a vapor, that's called sublimation, and from vapor straight to ice, that's called deposition. Yeah. Specific latent heat. So during that process, the latent heat, L, of a substance is the energy required to change the state of a unit mass, so that's 1 kilogram again, of the substance without a change in temperature. So how much energy is required to take a certain amount of that substance multiplied by the latent heat, and you use this calculation in questions. So really it's quite a straightforward process, quite a straightforward concept, and you just will need to apply this to some questions and work out what's going on. You may well see these questions given to you looking at graphs and having to infer certain things from the graph and work out what the rate of energy transfer is, or that sort of thing. But yeah, the idea is simply that for a change of state there is some latent hidden heat that is required to make that change. Where does that energy come in? Well, it's probably, so look, if we're going from our ice where we've got no potential energy, when we actually come then to a liquid and we've got a larger degree of separation and we don't have the uniformity that we did there, that energy has gone into increasing the potential energy. So it's taken energy from the surroundings, it's got an increased potential energy, and that's, yeah, it's overcoming and changing it so that it's no longer in that liquid state. Then again, the increase in potential energy inside our vapor, same thing happens. That latent heat goes into overcoming that boundary. And that is that. We've looked at thermal energy and what it is. We haven't done any calculations, but you can do those yourself. Can't be bothered. You want to do those. You want to get a bit of practice. And we've discussed what temperature is. We've looked at what specific heat capacity is and come up with a definition for it. And we've looked at what happens in a change of state and this equation here. We've got the change in energy. I don't know why my little mouse thing's not working now. Anyway, there we go. Where the change of energy is equal to the specific latent heat and the mass of the objects. That's thermal energy, and that is a wrap. Job done.